Welcome everyone. My name is Yahav, and I am a solutions architect in AWS. Together with me, I have Sami, who is database engineer in the RDS team. And together, we're going to talk about buffer content locks. So before we start, I wanna spend a few minutes about why we did this work. In the last 2 years, we noticed customers complaining about this buffer content locks and spikes of buffer content locks, lightweight locks that turn to be problematic and problematic in a way that they impact the customer applications. So, and we started to look for material and reference of other issues that people had, and there was none. There was few anecdotes, but there was nothing that could give us a hint on how we can help customers. So what we've done, long story short, we solved the problem, but then we wanted to contribute back our learning with the community. So what we've done, we build simulation. Some of the people here helped. Some of the people there helped to build this simulation, and we came up with some patterns that we applied that turned to be really helpful for these customers. So together today we're going to talk about this simulation as a proxy for those customers, because we cannot reference them, and share the patterns that we've done and how we help these customers to solve those issues. Okay, so we're going to spend a few minutes. Okay. I said loud. This can be that I just did not disable my notification, my ring notification. But let's spend a few words about few minutes about the workload simulation. So we've built some sort of last mile delivery system, right? That it's fairly simple. You have users that placing orders in the system, and then there are actors within the system that can fulfill this order. In this example, you have this driver that picking up the order and update the status of the order. From database perspective, user placing inserts of new order. This insert is also placed in some queue, waiting for some processing, and then there are sequence of updates to this inserts, right? And it's all a time series data, right? So I hope that makes sense on how the schema, right? There was no complex schema here that included lots of relations, etc. Although that was the evolution. We did had this issue initially, but that was one of the optimization points that we're going to talk about. And the workload simulation looked like that. We basically created this load of inserts and updates, etc., in a kind of a sine wave that goes on and on, and the load generated up to 50% of the CPU, just because that we wanted to let the system not to be too stressed, so to eliminate some of the factors that might be not relevant. So we allowed the system to grow up to 50%. And you can see that the number of commits that was doing, and when we talk about commits, I'm talking about everything. I'm talking about inserts, selects, and updates. That went up to roughly 10K at the peak. And by the way, we still run this workload. So if you have questions and want to see these things in action, we're going to see it. So we have it already running in a demo. All right, so let's now talk about the findings. So the first thing that we heard customers are asking us, okay, we want to first of all need to predict, or not to predict, to know when this thing's coming. Because before that, they were just experiencing the throughput from the application side, but there was not a good indication for them to know that this buffer content locks are coming. or these contentions are coming. So we're going to talk about how we are suggesting to monitor those logs, and these are also going to be a pattern, can serve a pattern for not just this log, for other logs. And then the rest of the presentation going to be focused on the two patterns that we found most effective. The first one is keeping the relationship size optimal of your database, and the second one is managing the database connections. Okay? It all sounds simple, because it is simple, but it took us some time to go and see how this, what does it mean? What does it entail to go and keeping relation size optimal and manage database connections? So let's jump right into it, and Sami going to take it from here.
Yeah, so before we dive into the findings, let's talk about what buffer content locks are. And buffer content locks are a type of a lightweight lock in Postgres. And lightweight locks are used to control access to shared memory. And in particular, buffer content locks are used to control access to a buffer in the shared buffer cache of Postgres. Now, this type of lock can come in two modes. There is the exclusive mode and there's a shared mode. In general, when a backend intends to modify a buffer, it'll take a lock in exclusive mode. If it intends to just read the buffer, it'll take the lock in shared mode. This type of lock is constantly happening in the database. So every time a buffer must be accessed, a buffer content lock has to be taken in one of two, in either mode. And really the only instrumentation that we have to see that this is happening is the wait event column of pgstat activity. If a process is waiting on a buffer content lock, you would see a buffer content wait event in pgstat activity. And most of the time, it's a non-issue for your workload. But then when you start seeing this wait event as the top wait event, that's when you also start to experience drastic reduction in your throughput and just an overall overall slowness in your database. So when we started engaging with customers on this particular issue, the first question they would ask us is, number one, how do I monitor for buffer content lock wait events, and how do I identify the SQL that's causing this specific wait event, and so I can take back that SQL to my application teams and go find a solution. And we found the most efficient way to do this is to use, if you're running obviously in Aurora, you can use CloudWatch. And what we have here is a anomaly detection graph, CloudWatch graph. And as you can see, the blue line represents a baseline of a metric called dbload non-CPU. Now, dbload non-CPU represents all the wait events that are not on CPU in your database. So as you can see here, there's a baseline, and your database is constantly below a certain threshold. But then, all of a sudden, you get this spike in dbload non-CPU. And based on this, you can set up an alarm. The DBA sets up an alarm, and they get paged. And essentially, the next thing they're going to do is go into performance insights, and they can correlate the spike that they saw in the anomaly detection with the spike in performance insights. And as you can see here, buffer content locks represents a major, part of our wait events. And you take that spike, you zoom in on it, and then you're able to essentially find the query or the insert statement or the delete or whatever the statement is that you need to focus on and you need to go fix.
So before we move on, I want to show you the system in action right now. Okay, so this is the This is the load that is currently running. You can see that it's the same load as we capture when we compile those slides. And if we're going to just zoom on the buffer content, look, you can see that this system experiences these spikes regularly, right? And if we look at the view of the database, the DB load non-CPU, you can see that there is a strong correlation between the buffer content lock and the time that the DB load non-CPU cross the normal values. So hopefully this is a point to make about how to monitor a buffer content lock. And so, the key takeaway from this pattern is to try and identify metrics of your database that changes, right, as a result of buffer content lock, but quite frankly, other locks, right? And see if you can correlate that. And if once you have this correlation, you can take advantage of CloudWatch and CloudWatch Alarm and and implement a similar concept. Having said that, that's not limited only to CloudWatch, Aurora, etc. You can still implement something similar with the system, the monitoring system that you choose to use. And this is just, again, an example. So now, before we move on and talk about the findings, right? Until now, we spoke about how to monitor it. Any questions about monitoring? Yeah.
So you see which query is impacted so far, but have we figured out why? Like, usually it's a victim, not the cause, right? So will we talk about how you correlate it to who's blocking here or who's holding the shared buffer lock? Will we go into how you identify it?
Well, yeah, so there isn't really, so one of the things about lightweight locks is there's really no instrumentation on the database level. I think you can enable some debugging, additional debugging for that. I'm not sure, but I remember seeing it. But essentially, there's really nothing that you can get out of any of the PG stat views that will give you, a hint. Which
You're
is
trying to correlate eventually.
yeah,
Right.
and so which is that, and that's why this was kind of a complicated weight event to solve. So actually what we're going to talk about next is essentially the patterns that we saw with various customers where we ended up resolving, resolving is kind of a strong word, where we actually reduced, mitigate, or like minimize basically the double for content locks. But yeah, so there isn't really much you can do besides getting that query and examining it.
Yeah, but really the important part here, back to the question that you ask, is that this tool or this method help to facilitate a conversation between the application and the database and look into this problem together. There was no like a point like, okay, you do this wrong, right?
And it kind of gets you, an answer quicker than like the application teams trying to figure out what's happening and the DBA trying to figure out what's happening. As soon as the DBA gets alarmed, they're able to start making, this within minutes they could have, they can identify the SQL, send it back to the application teams.
Yeah, and I think that in our case, we were the team, the Aurora Postgres team, try to add all kinds of instrumentation to, give you the right root cause and not the victim, and it's hard. It's hard because it can be all over the place. So yeah.
Yeah. So now you've identified the SQL. So what do you do about it? That becomes the next important question. So working with a few customers that experience this, we came up with some guidelines around what you should, what you should look for, and these guidelines are these patterns are what we saw as the most common root causes for excessive buffer content locks. So the first one is unused and duplicate indexes. And this, in my opinion, is a lot of the time is kind of a low-hanging fruit in your application. If you have a lot of unused indexes that are constantly being updated, in your right workload, but you're not using them to serve any reads, you need to basically drop them. So if you're reducing the number of buffers that have to be touched per insert operation or update operation, you're essentially reducing the load or the overall volume of buffers you have to touch per operation. By doing that, you're going to reduce the buffer content locks. So the low-hanging fruit is usually, do I have any unused indexes? Do I have any duplicate indexes? And if so, I need to get rid of them. And a lot of the times you have to look at, even if an index is used, can you do it? Can you work the application to avoid using, this type of index? I think one customer we worked with had like 175 indexes, and like half of them weren't being used. Dropping those indexes really helped out their workload dramatically, and they stopped seeing the buffer content lock scenarios. The other one is partial indexes. And especially if you're migrating from systems where partial indexes are not a feature, people tend to forget that partial indexes play an important role in Postgres. And partial indexes essentially allow you to index on a predicate, meaning that you can reduce the size of your indexes. A good example of this, if you have like an orders table and you have a status column, and 99.9% of your orders are completed and you don't need to reference them anymore, but 1% or less are in progress, and you're constantly checking those orders. Are they still in progress? Having a partial index on that column helps, because the index is now smaller, it has less buffers, and every time you're doing an update, you're touching less buffers. Therefore, you're not going to have as much contention at that point. The third aspect of this is foreign keys, and with foreign keys, what we saw is, particularly when you have a parent table that has very few rows, and a child table that's insert or update heavy. The scenario there is every time you modify a child row, there has to be a shared lock taken on the parent, and that shared lock requires a buffer content lock. And if you have a very narrow set of buffers that are being contended for, you can really start experiencing very heavy buffer content locks at that point, because those buffers that are holding the parent rows are constantly being hit by your workload. Now, I'm not going to say that you should go remove your foreign keys, but one of the advice we give is go examine if you actually need these foreign keys, and try to see if there's ways around it. The second thing is read replicas. So, like I said earlier, when you have contention on buffers between the shared mode and the exclusive mode, moving your workload moving your read operations to a replica, if you can, reduces that contention. And there's one specific case that I saw with the foreign keys, moving the queries that were querying the child table actually reduced buffer content locks. We moved those those queries to the replica, and we saw a huge reduction in buffer content locks. And the third point is the one we're actually going to spend more time on, is partitioning. But before I go further into that, does anyone have any questions?
So before we move, 1 second. Before we move, so if you think about this this order of thoughts, right? It aligns exactly with the process that we went with when we helped our customers, right? You sit in a war room, right, where everything is falling apart, and then people like Sami and other support engineers looking at all those things, right? And that's how we discovered those things. We found that this is how we discovered this suboptimality, right? And so we did those things, and we actually reached the point, the partitioning, where we were already stabilizing the system to some degree, but there was always another bottleneck that was uncovered. So yeah, I just wanted to spill some of the drama as we went through this learning.
Yeah, and so with partitioning, it's really interesting. So we ran our simulation for maybe a few weeks or months. I forgot how long it was running, but it grew into the terabytes. And what we started experiencing, and we were very happy to start seeing this, is the buffer content locks. All of a sudden, our non-partition table starts experiencing these very long spells of buffer content locks that kind of match up with the spike in the workload. So we said, okay, our next step at that point was let's start with a partitioned workload, a partitioned schema, and let's run the same workload for the same amount of time and see if we're able to reproduce this pathology. And as you can see on the left-hand side, we didn't. So what we do see is more CPU, just because obviously you're actually doing more work at that point. But we didn't see the spikes that we saw with the non-partition table that grew into the terabytes.
Yeah, and another interesting part is that, if you can go back, is that even before we partition, we were scaling up vertically the database. So what you're looking at DB at the 24 extra large instance, right? This is the largest instance. But if you downscale the instance, you could see those issues manifest much quicker. And why is that? Because basically the hot data set that we were trying to fit in the writer just did not fit. And that's caused all the things that we are discussing. And like I said, it's fairly simple, but it was not trivial to uncover that in a retrospect.
Yes.
Okay.
Was the simulation update heavy, or was it also just mostly insert?
It's updates and inserts.
Did you experiment with page fill factor?
Yes.
Yes, good point.
I would say fill factor gives you some relief, but it's not going to solve your problem totally.
So this is the distribution. This is actually from the live, the simulation that we're currently run, right? So you can see that the amount of inserts are fairly similar to the amount of update, just because that we decided that we're just going to pull the inserts, do update, and we're going to seal the transaction. But in the customer cases, it could be 6 times, right? It really depends on the workflow, the application workflow.
Yeah, and just to go back to your fill factor question, we actually had a customer, when they first reached out, what they were telling us is like, as part of their run books when this was happening, is their engineers were modifying fill factor for indexes and tables. And I think they had some success at some point, but then after a while, that run book just wasn't working anymore.
So one of the critical parts here is that there are many parts of the system that require the buffer content lock, one of which is the clock sweep algorithm, which is what's used to find a victim buffer to evict when you need to read a new page in that's not in shared buffers. So by decreasing the fill factor, you're increasing your working set size in terms of number of pages, and you can actually shoot yourself many times a page has been used. So every time you access a page, that gets incremented up to a maximum of 5. Clock sweep comes around, decrements that. You end up with this, it's a race. If you have too many buffers that are being accessed too frequently in shared buffers, it becomes very hard for the clock sweep to actually drive that count down to 0, which is what it needs to say, which is what the criteria is for. I have a victim.
Yeah, and that's in particular for index pages, because there's, you know, in the code path there's parts of the index where, or like basically if you have to split an index, that buffer content log has to be held for much longer. So yeah, couple that with, you know, a longer clock sweep, like, you know, Jim is saying, you can end up with this kind of pathology.
Right. So thus far we talked about how to keep your relation size fit your relation size or hot data set within the instance size. But there was another interesting point that we found, which is about managing the database connections. Now, there are several ways to manage database connection. We talk Postgres here, so PG Bouncer is one of the famous way, but not only. AWS offer RDS proxy, which is a similar concept, and what we wanted to achieve with these two solutions, I'm just jumping to the end and starting from the end, is that you want to minimize the connection churn, right? Because the application on one side is doing its right thing, and specifically about the applications, the customer application that we've dealt with is that they were using the Django platform. So the Django connection puller is very naive. It basically, if it wants to do an insert select, just do the insert, open a connection, and then once it's done, it's closing the connection, right? That's a good thing on one hand because it's very lean. You use what you need. But on the other hand, every connection that you open and close creates a context switch on the database side because that's how Postgres manage its connections. So that's one of the. I just realized that it's your slide, but I'm sorry. So that's one of the things that we wanted to reduce and measure in our experiment, and also the second part that we learned is that we wanted to limit the database connection pools. Right? Think about the connection pool as a potential surface attack to your database, right? And how much chaos you're inducing by opening connection and closing connection. So by reducing these connection pools or limiting the connection pools while you are adhering to the throughput that your application needs was very effective in reducing this.
And more specifically, when we talk about reducing connection pool, what we're actually saying is reducing the upper limit of how many connections, you know, your connection pool can establish. Because if things slow down on the database or things slow down on the application, your connection pool's reaction, not the reaction. Basically, you know, you get a request saying I need a connection, and if the connection cannot be given to, you know, back to the request, your connection pool is just going to open up, more connections. So you end up with like a connection storm. So what you really need to do is limit, you know, your max number of connections, and what we usually say is keep that in the hundreds, you know, up to 1,000, you know, on a Postgres instance. Once you get over 1,000 connections, you should start really re-examining why you need that many connections. So really set an upper limit on your connection pooler is good advice, and not just for buffer content logs but it's in general for to reduce any type of contention on your database.
So what we see here, this is actually an example of how connection pool can help you, regardless to buffer content locks, right? You can see that there is no so much buffer content locks in this case, right? We're going to look at another example in the next slide. But what we found here is that when we let Django, the naive connection puller on the client side, do its work, like opening connection every time, and it's and the load is acceptable, right? It's not overwhelming the system, and the system is fairly stable. You can see the green part, which is a lot of CPU, and that's the context switch that Postgres does when it's open and close new connection. And when we just placed the PG bouncer in front of it, we just saw immediately that this CPU went down, and basically Postgres spent more time in the exact sync, basically flashing those transactions to the storage, which is what we wanted to get, right? So once we've seen this type of behavior, we say, okay, now we're going to increase the load, and we're going to push the system into its boundaries.
Just 1 second.
Sure.
So the interesting thing here is, even though your exact sync wait events are much higher, and your CPU is much lower, if you actually look at the transaction throughput, you're actually getting more transaction throughput once you introduce, the PG bouncer, or a connection pooler, for your application.
Absolutely, yes. I forgot to mention that. That's the most important thing, the throughput. Yes.
What are the green and brown wait events?
The green is CPU, and
Exact sync.
and the brown is exact sync.
Got it, okay.
Yeah, it's hard to see it. Yeah.
So for anyone not familiar, exact synced means that you're committing your transaction. So on a system that's doing a lot of transaction throughput, you can see a lot of those waits, because you're basically just waiting on the I/O subsystem to say, yes, I've got your data. So that's not necessarily a bad wait event system.
And you can tune it, you can tune it by batching if you can, but in general, if you're achieving your throughput, then it's usually something that you shouldn't be too concerned with.
Yeah. So the throughput really went high when we started to when we used the PG bouncer, and it was the same workload, right? The same insert and update and all that. Now, so when we accelerated the load, then we started to see this thing, right? Again, without a connection puller without connection puller. Again, this is the CPU that we've seen before, but when we pushed it, we started to see immediately these buffer content locks ramping up, right? And like you can see here, the CPU was growing. Yeah, and yeah, that's what makes us make us the understanding that, okay, if we're gonna bring this load that we spent here, that we generated here with PG bouncer, this is what we saw, right? And you can see here the exact sync was replaced by replacing by the CPU. You can see that the CPU was still doing things, but again, the throughput, like we saw before, was much higher, and again, no buffer content locks that were impacting the application. Anything else we want to add here before we move to the?
Yeah, I just want to clarify what we mean by connection churn, because I don't think we defined it. It's
Sure.
basically a connection and a disconnection. Right. So if you're constantly connecting, disconnecting, that's connection churn. You need it's the good the advice is you should reduce that that count. Now there is a metric, I don't know if we show it here, for Aurora. I think it's called number of auth connections. I'll look it up, but basically there's a metric that shows you your connection churn, how average is basically.
Oh, I think I have it.
If you have it, let's show
And
it.
just to be clear, connection churn on a connection pooler is perfectly fine. They're built to handle that. What you don't want to have happen is that you're constantly connecting and disconnecting from the database itself.
This guy.
Yeah, so auth attempts. There you
Yes.
go. Sorry, I forgot.
This guy. Yeah.
So total auth attempts, that's the average of how many how many authorized connections are established for that data point. And what you really want to see is, you really want your application, when you start up the application, you want to see that number, you want to see that number go up, but then to kind of like steady out and, be much lower than when you started up the application. Because at that point, you have established connections in your pooler and you're reusing them.
Yeah,
One question I've had, and it's a little bit of a tangent, but
sure, we love tangents.
PG Bouncer, for example, when it's done with a session, it will do something like discard all, right? I've not been able to find, or have I experimented with this. Does that deallocate memory that was allocated? Like if you have a session that happens to have increased workmen, for example, through the pool, should you avoid using the pool for sessions that will maybe use non-default memory settings, or if it's allocated a lot of memory to that back end?
No.
That back end could potentially continue through its life cycle.
Well,
That's one reason.
that's, what discard all does is say, reset all the settings. That does nothing in terms of memory allocation. Now, something that we have seen is that as a backend gets older and older and older, it can have memory fragmentation maybe is not the correct term, but roughly something akin to memory fragmentation, where a backend can slowly be consuming more and more memory.
Like glibc's malloc fragmentation?
Well, I mean, Postgres specifically avoids malloc. It has its own palloc implementation. But yes, you can end up with the palloc arenas are skewed and all kinds of stuff can happen. So most connection pools allow you to set a maximum age for a connection. So once a connection hits a certain, and I've seen wall clock, I don't know if any do like number of statements or anything, which is actually probably more important, but you can basically say, look, any connection that's been open for an hour, just drop it, and then the pool will establish a new connection.
And is an hour pretty reasonable, you would say, for? I mean,
I've never
generally?
really dug into it. I mean, I think it's going to depend somewhat on your workload. One starting point there would be to just say, okay, if I have 100 connections to the database, then if I say don't let anything live longer than 6 minutes, if I'm doing the math right, that means you get 6 new connections per minute. So I do the math, but the point is that as a lower bound, you can do the math to say, look, if I set it to this and I know that I've got 100 connections, like how many new connections to the database will I get per minute? And you want to keep that reasonable. That said, I mean, if your connections are not doing a tremendous amount of workload, 30 minutes, an hour, and this is, I'm trying to think of what a good metric for monitoring the memory consumption of the back ends would be.
Freeable memory and swap space, I guess. I mean, you can see the overall instance allocations.
Yeah, but those are tricky just because it's going to be everything that's being used. So if a query's up and running, which you can, if you look at enhanced monitoring, and if you look specifically at backends that are idle and see how much memory they're using, that's the thing that you're actually want to be looking at here. Is when the backend's just done, and especially idle, not idle in transaction. If it's just sitting there idle, it's like, okay, it's not doing anything. And when it first starts up, maybe it's consuming, I don't know, 5 megabytes. And over time, you can see, well, maybe it's got up to 7, 8, 9, 10, 15 meg, which 5, 10 megabytes extra isn't that big of a deal. But when you start multiplying it by the number of backends you have, suddenly that becomes a much bigger number.
Yeah, and that's a good question, and yeah, look, we don't cover it here, but yeah, recycling connections is kind of it's an important topic, and usually we talk about that when customers are facing like out of memory situations or they're running low on memory, and the advice I've worked with a customer once that had connections open for days, and kind of did what what Jim is saying, basically, there was just a lot of memory that was being reserved for that process that wasn't going back to the OS. You recycle connections, you start recycling, and I think we told them to recycle every 6 hours or something, as a start. But they started noticing that they weren't really dropping, their freeable memory metrics weren't dropping as fast, or dropping so low and staying and staying that low. So yeah, recycling connections is actually a very good. It's a very good thing to do. And yeah, we don't talk about it here, but.
And I think we experiment that in that context. But again, this is just probably just dropped when we were doing this this activity. Now, what I wanted to spend a bit more is to demonstrate the point that Sami made about the total auth attempts, right? Okay, so I brought up another simulation that I'm running, right? So there is one simulation that runs with no database connection and puller, right? It's just go directly to the instance, and this is what you see. It's fairly similar workload, right? I think that's even a smaller instance. Even a smaller instance. That's a DBR68 extra, much more smaller. But but if you look at the amount of total auth attempts when you just let Django, the application connection puller, to do its work, right? It's running at 50K, right? When it is trying to insert to make a 5K commits. Remember, we talked about 10K commits when we started this thing. Okay, so this is half of the capacity of the original one. It's opening 50K auth attempts. And if you go back to the experiment with the connection puller, this one is with RDS proxy with no PG bouncer, but that's a long story. But you can see it's fairly similar, and you can see here that the auth attempts jumps to 200, right, at the peak when the system was stressed. So that's another point to emphasize why connection puller in any kind will just be a good exercise, good hygiene to adopt.
Yeah, and I just want to clarify. So auth attempts, that metric itself is Aurora specific metric.
Oh, okay.
In community Postgres, you can enable log connections and log disconnections parameters, and you can basically analyze the log files or use like a PG badger, which gives you that detail. Postgres 14, not 13, I think 14, in PG stat database, there's 3 new columns that basically have countermetrics for authorization. So that's something you can now take advantage of in community Postgres.
All right. So the last thing we're going to talk about with respect to database connections is that we said, okay, fine. So the database, the PG bouncer is good. It's worked pretty well. But we wanted to further optimize, right? We were able to reduce. Sorry, I need to talk too close to there. So we were able to reduce the buffer content locks, right, to an acceptable level, but it's still, we wanted to push it more. So what we've done is, instead of increasing capacity, we reduced the capacity. We took the number of database of the PG bouncer instances, containers that were proxying those connections, reduced it by half. And by just doing it, we were able to get more, right? So when we say getting more, look at the, you can see that it was actually, the buffer of content locks was removed. The layer that buffer content locks we had here removed completely. And you can see here that the number of connections, you can see that it was reduced. So it didn't give us like a significant optimization, but this was just to prove that that adding more things to your system does not necessarily going to help you, right? So
I mean, the interesting thing up there is, regardless of how many, so if you look on the left-hand side where we have more connection pools, we actually have the same amount of inserts and updates as the right-hand side. So having 15 PG bouncer instances all configured the same way versus having 5 PG bouncer instances, pretty much gave us the same throughput. So, you know, so the question becomes, or the observation here is having more connection, more PG bouncers and essentially more connections is not gonna help you increase throughput.
What's the light gray wait event on the left? Between the green and blue, whatever color that is.
This one?
Yeah.
Lock extend.
Oh, it's probably extending the data
Lock
file.
extend.
So that's on that's when you're trying to extend the relation files.
Oh, it's a relation.
Yeah, lock extend is the wait event when you're. So I think the table gets locked when you're trying to add more pages to the relation.
We pinned down what it was about connection count that causes this behavior.
I think there's an optimization around how many pages. I think there's a heuristic where, like, depending on how many backends are running.
Yes.
Yeah.
Yeah, so the number, it's roughly, so if you're growing a relation, you need more pages in the relation. Doing that page by page by page can get very expensive.
Mhm.
So the system will look at, I believe it's how many running processes there are.
Yeah.
And it uses that to scale out how many pages it allocates
Yeah.
at one time. But I would say that this is a performance optimization and this is worth doing because even though this did not give you more throughput, if you look at those two wait event graphs, I mean, the one on the right is way more stable. Like, I would much rather have my production systems look like that
Yeah.
than the one on the left.
That's a good point.
Judy.
That was my question.
Great mind thinks alike.
Tough one.
All right. So key takeaways. That's what we want to. So we want to convey that you should monitor your buffer content loss and, quite frankly, any lock. Try to see what is your with your favorite with your favorite monitoring system, CloudWatch in our case, and just think about how you triage this type of issue beforehand, like the method that we showed with the anomaly detection on the specific metric. Later on, instrumenting that with performance insights. And then keep the relation size optimal, clean unused relations, add read replicas, and partition your tables, right? Again, if it's time series, of course, in like our case. And then use connection pooler and limit the pools. And then this is last but not least, latest version. Use your latest version. Keep your database updated as much as you can. Don't let it linger because then this major upgrade is going to be much more painful. And again, the latest versions always includes optimizations like index optimization.
And specifically Postgres 13 and higher, there's optimizations around duplicate index values. Essentially, instead of indexing each value, now it's basically kind of like aggregated. So it reduces the index size, and like we said earlier, keeping the index size smaller and keeping your relation size optimal is going to be very beneficial. And Postgres 14 has optimizations around connection management. So these are kind of very two important things. And so I recommend going to 14 if you can, if you have a new application, because you're going to get some really, really good optimizations.
Do we expect to see that this year for Aurora?
Postgres 14, I don't know, not sure yet if it's released.
And finally, try it yourself if you like to simulate this load. We open source that. It's fairly simple, all Bash, no special, not even Python. It's super simple. You just take this bash and deploy it as Docker container, and you fire a Kubernetes cluster that does everything for you. So yeah, that's what we have for today. Thank you very much for everyone. Yeah,
Thank you.
we are on time, right? Wow, amazing.